finishing up the practice test here. Also, for the most part, everybody did good on the rectangles too on number 1, so that was good. All right. Okay, part A says if A is the area of a circle, so we need that formula. A is the area of a circle with radius r, and the circle expands as time passes. Find dA dt in terms of dr dt. It's a little confusing to me the way they've got that worded, and then they've got the dr dt stuck over there by the end of the answer box. It just seems like it'd be easier if they just said find a formula for dA dt. So all we're doing, we're taking the derivative of both sides with respect to t, with respect to time. So if we take the derivative of a, it just has a 1 coefficient, so we'll just get 1. But then we have a dA dt. And then on the other side, pi is just a constant, so it's a number. So taking the derivative over there, we would do 2 times pi. And then subtract 1 from the exponent, we'll get r. And then we'll have a dr dt term. Then on B, it says suppose oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1 meter per second, how fast is the area of the spill increasing? So how fast is the area increasing? That would be changing the area with respect to time. And it says if the radius increases at a rate of 1 meter per second, so that would be how the radius changes with respect to time. Dr dt, so dr dt is 1. We want to know what dA dt would be when the radius, when r is 34. So we can just plug in on this one, nothing too terrible. Not as bad as some of them were. Yeah, so we have 2 r, it says is 34. Dr dt is 1. So we're doing exact terms here. Got 68 pi square meter per second. So answer there. Or you could give a decimal. Questions and concerns on that one? Number 17 gives us an equation, gives us a function. Part A, we want to know the intervals where it's increasing or decreasing. So to check that, we need the derivative. So let's see, f prime. So the idea, right, it's been a little bit. The idea is where our derivative is positive, f will be increasing. Where our derivative is negative, f will be decreasing. We found our derivative, so let's see, it's 3x squared minus 18x minus 21. Just 3 applications of the power rule. And what we need to figure out where our derivative will be 0, and then we can plug in some test points in between those values and figure out where we're increasing or decreasing. So we take our derivative and set it equal to 0. One thing I'm seeing is we've got a common factor of 3 we can factor out. So I'm going to do that as I set it equal to 0. And you could do quadratic formula. This one's not bad to factor. So I'll divide both sides by 3. I'll get rid of the 3. And then we need factors of -7. So that when we add them up, we get -6. So -7 and +1. That means our derivative will be 0 at +7 and -1. I'll set each factor equal to 0 and so on. Then we need test points, and we're just trying to figure out the sign of our derivative on each interval. So we need a test point smaller than -1. What do you want to use? -2 sounds good. Okay, so we can plug it in here if you want to. You can plug it in any version of the derivative here will work. We'll plug in -2 here in factor form. We'll get -9 and then -1. So -9 times a -1 will give us positive. Positive on this first interval. We need something between -1 and 7. 0 is good. So plug in 0. What's it going to be? -21, yep, so it'll be negative. If you think about with 0, we can just go back here to probably the fastest. This will be 0, this will be 0, and we'll have -21. So it's negative there. Then we need something bigger than 7. 8. Okay. So if we try 8, I think the fastest place is in the factored form, so it'll be +1 times +9. That'll be positive. Okay. So we're increasing anywhere the derivative is positive, so we've got 2 of those intervals. What are they? Okay, -infinity to -1, and 7 to infinity. Okay. And then what interval are we decreasing on? -1 to 7. Yep. Okay. B part we can get from the same sign chart. Here we go. Remember, local minimum happens at a valley, so that would mean the local minimum happens where our derivative goes from negative to positive. The local maximum happens at a hilltop, so that would be where our derivative goes from positive to negative. So here we got shift from positive slope to negative slope. So -1 is going to be, well, yeah, local max. It's where it happens there. And then we go from negative slope to positive slope at the other one. So that would be local maximum. That's where the local maximum happens. If we want to actually get the minimum or maximum value, what do we have to do with those? Plug it into, yeah, we really want to plug it into the original function. And plug it into the original function. So we take these 2 and plug them in there and see what we get. So if we plug in -1, let's see, it's -1 -9 plus 21 plus 9. That gives us 20. And we're just finding f of -1. And then we'll do f of 7. If we do 7, that one not as easy to do. in your head. And if I typed all that right in, maybe I didn't. Let's see. Right, too. That's a weird max. Let me check the other one. Did I do the other one right? -1 -9 plus 21 plus 9. 20. Do we do these backward? Go from, oh, yeah, I wrote it down backward. We said it right, and I wrote it down backward. Because the minimum is going to be where we go from negative to positive, so it's going to be at 7. We just wrote, we got them both right. We said them both right. We just wrote them down backwards. Sorry. Nope. Yeah, that's right. This one would be. What was that? Negative 236. Is that it? Okay. Part C says find the inflection point, and I wish they would do it in the other order. We also want the intervals where we're concave up, concave down. So for part C, what do we got to have? You got to have second derivative. That's right. You got to have second derivative. So second derivative, so you will get 6x minus 18. Make us a little number line here. We need to know when the second derivative is 0. So you could set that equal to 0 and solve, or it's not too bad to see. It's 3. Now 6 times 3 is 18. Minus 18 will be 0. And then we need to do a test point on each side. So we try 0. We get 6 times 0 minus 18, so that'll be negative. Do something bigger than 3, so maybe 4. 24 minus 18, that'll be positive. Wherever our second derivative is negative, it's concave down. Wherever our second derivative is positive, it's concave up. And anywhere the concavity switches, that x value is a inflection point. So we're concave up where? Three to infinity. Concave down. Negative infinity to 3. And the x coordinate of our inflection point is 3, because it changes from negative to positive at 3. So any sign change, negative to positive or positive to negative, means the number where that changes is the x coordinate of our inflection point. And then this particular one also wants the y coordinate, so we would just find f of 3. We go back to our original function. So let's see, 3 cubed minus 9 times 9 minus 21 times 3 plus 9. I got negative 108. And math trying to get negative 1. Okay. Good deal. All right. Question on that one? Yeah. Yeah, and usually I just ask for the x coordinate, so you don't have to do that last step where you find the y value. You just give the x value. 18. Use the Hospitals rule where appropriate. If there's a more elementary method of finding the limit, we can use it if we want to. I got this limit, x approaches 7, x minus 7 over x squared minus 49. We try to do direct substitution. What do we get? 0 over 0. So what do we want to do? We can do the Hospitals rule. And the Hospitals rule says we take the derivative of the top and the derivative of the bottom, and that'll give us the same limit. So the derivative of x minus 7 is just 1. The derivative of x squared minus 49 is 2x. Then if we try direct substitution, what would we get? 1 over 14. Okay, so that works. Not on this one, because that only works when we're dealing with infinity. If we're going toward positive or negative infinity. That's a good thought, though. So, yeah. So that our other option here, I think the other good option is we could factor on this particular one, not always. Okay, but at the bottom is a difference of 2 squares. So the x minus 7s would cancel. Leave us with 1 over x plus 7. And then if we do direct substitution, we'll get 1 over 7 plus 7, so 1 over 14. Either one of those would be appropriate on that problem. I think the Hospitals rule is probably a little bit quicker maybe on that one. But I guess if you didn't actually write out where you were canceling, if you just saw how it would factor and you could just write this down as the next thing you wrote down, then it would be about the same. Okay. 19, same type of problem, just a different limit. So if we try direct substitution, it's pretty. We get 0 on the bottom. On the top, let's see, 64 minus 16 minus 48, is it 0? Yeah, so this is 0, 0 again. You do need to check and be sure, and because if you don't get an indeterminate form, if you don't get 0 over 0 or infinity over infinity or one of those indeterminate forms, then the Hospitals rule does not work usually. Okay. It's only guaranteed to work if we're in indeterminate form. So what do you want to do on this one? Yeah, we could. Yeah, it looks like on this one we could factor again. So we could do the top would be minus 8 and plus 6. So that would be 14. Or we could do it with the Hospitals rule, probably. Should be able to. To do the Hoppel's rule, we'd take the derivative of the top and bottom, so we would have 2x minus 2 over 1. And then we're not in indeterminate form anymore. We could use direct substitution. We get 16 minus 2 on the top, so we get 14 that way as well. Yeah, if it's a high pressure situation, it's kind of nice to be able to do both and see that they come out the same. Like a test. Questions on the Hoppel's rule? Yep. Plus or minus infinity, yeah. Because the thing that helps us there is because on those we use that special limit where we have 1 over a power of x that gives a 0, so it makes things simplify, and that only works if we're going to infinity, because if we're approaching some other number, 1 over a power of x is not going to be 0. All right. Got a definite integral. I didn't give you anything too ugly. This one is just reverse power rule. So here we're ready to go straight to antiderivative. We don't have to do any kind of algebra or anything. Well, I said go straight to antiderivative and wrote down the intervals. We don't have to do any kind of algebra or anything to get ready. So we add 1 to the square, we get 3. Was a coefficient of 1, so divide that by 3, we get 1/3. The middle term, we add 1 to the power of x, we'll get x squared. We had a coefficient of 2. 2 divided by 2 is just 1. And then with a constant, what's our last one going to end up being? Just minus 8x, yeah. And then we want to evaluate this from 7 to 9. Means we plug in the top number first, minus what we get when we plug in the bottom number. That was another thing I thought went really well. I don't remember seeing anywhere you got out of order, where you did like the 7 first or anything. So that's good. So let's see. This one's a little long. We got that minus. Yeah. So let's see, that's 9 cubed, 729, divided by 3, so 243 plus 81 minus 72. So that first group of 3 terms there gives us 252 minus let's see, 343 divided by 3 is a fraction, plus 49 minus 56. So that second group, it's a little uglier. I get 322 over 3. And then see whatever that is. Ugly. 434 over. I say ugly, at least it's rational. It could be. Could be root 434 over 3. It could be way worse. Can best try it, see if that's what you got. Yeah, okay, good. Alright. 21 is shorter because it's indefinite. We don't have to plug in any numbers, but we do have just a little bit of algebra we need to rewrite so we can use our reverse power rule. So 6 through to x to the 7th, what's that going to be? It's going to be x to what? Yeah, 7 over 6 power. And then our antiderivative will add 6 over 6, add 1, so it'll be 13 over 6. And then divide by 13 over 6, that means flip and multiply, so we get 6 over 13. And then it's indefinite, so we need a constant of integration. Let's see. If I remember right, that one went pretty well. The one that we had that was similar to that on the test. Questions on that one? All right, time for the arch nemesis now. Substitution. And tells us to use x cubed plus 21 for u. If we take the derivative to get du, that'll be 3x squared dx. So let me hang on. So that part's u. So the part we got left over is x squared dx, but we got 3x squared dx. So to adjust that, we can divide both sides by 3, or you could think about multiplying both sides by 1/3. Okay. So now this part is 1/3 du. So when we rewrite, we can put the 1/3 out front because it's a constant. The inside will have square root of u du. So here's that part. This part's u. Okay. And then just a little bit more work, we can take our antiderivative, we can rewrite square root of u as u to the 1/2. So for our antiderivative, we'll have 1/3 times, add 1 to the exponent, so you'll be 3 over 2, flip and multiply, so we have 2 over 3. We do have a, no, we don't have cancellation, we got 2 over 9, u to the 3 over 2, plus c. And u was x cubed plus 21. So we can undo that substitution. Question on that one? You just gotta work with them till you kind of get the feel for what you're doing. Seems like everybody that had a reasonable grasp on what was going on with substitution pretty well, did everything right. But it's easy to get confused in the middle of the problem if you're just not real comfortable with them. E3 tells us to use u equals x to the 6 minus 5. So if we do that, du would be 6x to the 5th dx. So if u is this part, the part we've got left over is x to the 5th dx. We've got 6x to the 5th dx, so we can divide by 6 or take 1/6 of that. Don't always have to do that, but on the two we've done, we've had to do it. So if we rewrite this thing in terms of u, we'll have a constant factor of 1/6 out front. The bottom is u. And then the x to the 5th dx, along with the 1/6, gives us the du. If we need an antiderivative of 1 over u, what's that going to be? Antilog of absolute value of u. Let's see. And then, almost finished, we'll just undo our substitution. So the whole point of u substitution is to be able to take, it is a little work, right, but is to be able to take some kind of garbage and rewrite it in an easier form, so it's easier for us to find the antiderivative. So like that's just one of our basic rules, and then we can undo it. Undo substitution. Okay. And then one more. Substitution, but we've got a definite interval. Okay. This one doesn't say it's substitution, but that's what we need to use on this one. Okay. It doesn't give us a u, so we've got to pick out our own. So what should we use for u? Yeah. Want to go with something on the inside. I think 1 plus 7x is the ticket there. If we do that, then du would be 7dx. So if this part is u, all we would have left over is a dx. We've got 7 dx's, so we can adjust that. And just use 1/7 of du. That'll give us just the dx that we need. So up to that point, we can write this. But since it's definite, and again, you don't have to do it this way. I think at least one person found the antiderivative this way and changed everything back to x and then plug the numbers in. That's okay. That does work. It's just a little bit longer sometimes. But the other way to do it is we use our u equation and take our limits of integration and change those into u's instead of x's. So we do the top one. Let's see, we'd have 1 plus 7 times 1. That would give us 8. And then if we do 0, we'd have 1 plus 7 times 0. That one would be 1. And Antiderivative, that's u to the 1/3. Right. So add 1 to that, we'll get 4/3. Flip and multiply, that'll be 3/4. And we can evaluate from 1 to 8. If we combine our two constants, and let's see, that's 3/28, and then we can plug in our numbers. So we'll have 8 to the 4/3 minus 1 to the 4/3. So 8 to the 4/3, I have no idea. So, 16. And we just need 3/28 times 15 gives us kind of an unsatisfying 45/28. There's nothing wrong with if you get to here and then undo the substitution and use the original limits of integration. There's nothing wrong with that. It's just you may be working a little bit harder than you would have to, because usually in terms of u, the thing's a little more simple than it is in terms of x. So when you plug in, it's a little messier if you're dealing with x usually, but either way is okay.
So if the final is our lowest grade, are you still going to put it in Canvas and it just like, how's that going to work?
The final will count, but if you make better on the final than one of your other grades, the final score will also go back and replace a lower test score, one of your lower test scores. So it'll replace your lowest test score.
Like my lowest history.
No. Other question? Yeah.
Are the questions on the finals probably going to be about the same amount?
It'd probably be a little shorter than the practice test. Okay, because that's a little bit long to do all in one test, I think. What do I have on 24?
When is it?
It is 1:30. Yeah, 1:30. I think something like that. Yeah, Monday at 1:30. Yeah, and being here. Okay. All right. Just the 1:30 day part. I don't know.
On those definite intervals where you have to use substitution, you're plugging in for like trying to get the upper and bottom limit on the interval sum. You plug it in for u, not x, right?
Yeah, you plug it into the u equation. You plug it in 4x into the u equation you have, and it'll tell you what it would be as u.
So you're solving it for x.
Well, you're plugging in where x is and solving it for u. Yeah. Okay. Yeah, that's a good question. Yeah. So I got I got a little lazy. I should have written u equals. Yeah. Yeah, because these are in terms of x. So you figure out if x is that number, what's u going to be? And then that way you can just deal with u from that point forward. Pick the one. Oh, good. Yeah.
One of them was like 0.7, the other was like 4.
Yeah. Anything else you can think of? Our last class, so no class Friday, right? That's final start tomorrow. And then yeah, that's probably the best thing. Well, we don't really have any dead time really the way it's set up. Tomorrow I'll just be in there most of the day probably. Yeah, they closed at 9. Yeah. Yeah, at 8. Yeah. And then I won't see anything till after finals. So, and then even when I do see it, I don't see what everybody put individually. So, all collective. All right. You don't have anything else? I'll see you on Monday, I guess. Guess I'll stop this.
Have a nice weekend.
All right, you too.